give everyone a moment to join us. Welcome, everyone. You are joining us for Metrology as a Mindset, Engineering for Success, presented by Optikos and hosted by Photonics Media. Today's speaker is David Biss, Senior Optical Engineering Manager at Optikos. With over 20 years of experience, 7 patents, and a doctorate from the Institute of Optics, David will walk us through how a measurement-driven approach to image quality, rooted in metrology and real-world lens projects, helps teams reduce risk, align design intent with performance, and achieve consistent, world-class results. We're also joined by Rick Skoglund, who will start off with a few words about Optikos. Rick leads industry outreach and brings a strong background in both engineering and business, helping bring Optikos' optical expertise to a wider market. A quick note, feel free to ask questions in the chat at any time. If you experience technical issues, try logging out and back in. You'll receive a link to the webinar recording in your inbox after the session. With that, let's welcome Rick Skoglund and David Biss.
Thanks, Haley. Good morning and afternoon, everyone, and welcome. We're excited to have you join us today for this special session. Before we dive in, just a quick word about Optikos. For those of you that are not familiar, we've been in business for over 4 decades, and Optikos has been a leader in optical and optomechanical engineering, helping companies turn complex optical concepts into reliable manufacturable products. We combine deep expertise in optical design, systems engineering, and metrology with hands-on experience developing instruments for markets ranging from consumer imaging and industrial sensing to aerospace, defense, and medical devices. At Optikos, we think about metrology as a mindset, obviously the title of this webinar, not a final checkpoint. It is a foundational discipline that shapes how we design, engineer, manufacture, and validate optical systems. Metrology as a mindset means measurement-driven decision-making is embedded from concept through production. For our customers, this translates into proactive risk reduction. We identify and mitigate design and manufacturing risks through rigorous validation and verification, leveraging our industry-leading image quality metrology expertise. Furthermore, we deliver measurements they can rely on using our benchmark standard lens and camera testing platforms, precisely configured to their specific application and performance requirements. And for on-demand needs, our state-of-the-art optical metrology laboratory called IQ Lab provides comprehensive camera and lens testing services, supported by decades of hands-on optical engineering experience. Ultimately, our metrology-driven approach allows our customers to make decisions faster and move programs forward with confidence. And now, without further ado, I'd like to pass the floor over to David, who will explain our approach in more detail.
Hi, everybody. Thanks, Rick, for the intro there. Again, I'm Dr. David Biss. I'm the Senior Manager of Optical Engineering at Optikos, and I'm going to be your host and talking about metrology as a mindset. I'd like to sort of start off with a quote here that I don't know who said it. I feel like I've heard it a lot, and if I talk to people in industry, I think everybody has a similar version of this that they've heard, is if you cannot measure it, you haven't made it. And that's really sort of at the core of this metrology as a mindset. I'd like to take that a little further and say, you know, when you're doing a development, you sort of have a choice. There's sort of 2 paths, you can take. You can take a path where you consider little to no metrology for your system or your qualification of your system, or you can consider a robust metrology path where you have thoughtful design, measurement techniques, and kinds of measurements that are going to lead to success. With little to no metrology, you can only speculate about problems, and I'll talk about that. If you don't think about metrology ahead of time and it comes down to sort of the end of the project and your crunch time, you're going to need to develop a testing plan. And often, you're going to need some custom tooling. And so with little or no metrology, you run the risk of losing time and money during a development or in a manufacturing setting. With robust metrology, at the time, it can feel like it's going to take more effort, but it'll help you troubleshoot. It'll provide more consistent results. And with consistency, you're going to save time and money. So really there's a bottom line here is that a metrology mindset is going to save your project. You're going to reduce confusion during the build process and troubleshooting. You're going to get more consistent prototype and production outcomes, and you're going to have less downtime, and you're going to save money. And who doesn't want to do that when you're either doing a development or you're in a production mode? Now, I'd like to throw up sort of our development roadmap we have at Optikos. You know, a lot of people have similar types of phase developments. You have sort of a pre-development or feasibility proof of concepting phase. You have your what we call development, where you start creating prototypes, your alpha prototypes, your beta prototypes, and then there's your manufacturing phase where you do your transition into manufacturing and start producing product. In my experience, a lot of times people start thinking about metrology around the transition from development to manufacturing or at the end of a prototyping phase. And I think that is not the best way to look at things, and is really comes down to this metrology as a mindset talk. Really, and what I'm going to talk about here is that you should be thinking about this all the way at the pre-development, as soon as you start developing specifications and really thinking about the thing you're going to make. It's helpful to start thinking about how are you going to measure that thing when you get there, when you start this initial development. So I would take this sort of development roadmap and sort of break it into sort of 3 different rough categories, where we talk about, you know, sort of in the early development when we're developing specs, maybe thinking about doing our preliminary design. What am I going to measure during this during my prototyping and manufacturing? And then, you know, when I'm doing my design work and preliminary and critical design, you want to start thinking about, how am I going to measure this? What tools do I need to have on hand? What tools do I need to create? And then when you make the leap from development into manufacturing, you're going to want to start thinking about, do I have enough metrology? And, you know, do I have enough? Do I have too much? Do I have the right mix of metrology for my manufacturing process? Now, with that, I'd like to talk about, you know, our experience that we've had at Optikos and our customers have had with talking about what am I going to measure. I'd like to start that off with sort of a quote that and it's really a comment or question I had received when I was giving a talk, where I had talked about determining metrics for system performance, and someone commented that, you know, we've run into a problem multiple times where we'll build an optical system and then we'll test it. And so we've done all our development, we'll test the system, and we'll find out the performance is lousy. Then you have to go through a lot of pain and do a lot of troubleshooting, and they figure out that a subassembly in their system, which they had made a lot of assumptions, and in some cases it makes sense to make those assumptions, but they assumed it should perform at some level, and it turns out that it doesn't perform at all to the level at which they were expecting. And so that sort of ties into this, what should I measure? And clearly in the case of this quote, the idea is like, well, they should have considered measuring this subassembly in the system. And so I could take an example of just a simple microscope lens design that I have up on the screen here. And I think everybody would agree that for a lot of microscopy applications, resolution is the key thing that people are interested in. How well can you resolve these small features? But leading up to this sort of final test of resolution in the system, you're also going to want to consider testing other parts of this assembly. You may want to think about, well, how am I going to test this objective? Or what about the microscope objective would I want to test? Do I want to look at wavefront? Do I want to look at MTF? Do I want to look at some other parameter, field of view, focal length? There's transmission. There's a lot of different parameters you can think of. And sort of along with that, you can also look at the tube lens. If you have a objective tube lens pair in your microscope, you're going to ask a lot of the same questions. Do I want to measure wavefront? Do I want to measure MTF, transmission, other things? And then other components in the optical assembly, you're going to say, you know, if I have beam splitters or dichroics in the path, do I want to look at the transmitted or reflected wavefront of these guys? Do I want to look at spectral transmission to make sure the right spectrum is passing through the system? And by thinking of these components and sort of thinking about what you want to measure about these components, you're really trying to sort of build a base of component metrology or subassembly metrology that is going to yield your final system performance. And so it's sort of like these are the different building blocks that are going to create this, in this case of this cartoon, this house that then you've built a lot of confidence that the system you've constructed is going to have good performance at the end. Now, if we want to think just generally about, well, what am I specifically going to measure in an optical system, I think there's sort of two ways to look at it. There's a very straightforward, simple set of metrics or specifications or things about the system that you would want to measure. And then there's another layer that's a little more complex in terms of looking at system metrology or subassembly metrology or component metrology. When we think of what I'm going to call simple metrology of a system, we're talking about, you know, it's if you had a lens and you have all the a lens assembly, and you have all the parts in front of you, and you put it on a table and you say, hey, what metrology are we going to do? I think this is the first thing everybody would think about. Oh, we have mechanical components, so we can measure the mechanical dimensions of cells or barrels or retainers or the fit of the retainer. And then if we have lenses, oh, let's think about the center thickness of the lens or the clear aperture diameter of the lens or the radii of curvature or surface irregularity or something like that. And those are all valid things. You want to do incoming inspection. You do want to measure these different components. If we take it a step further and we think a little bit more about what might be a little more complex, or what I'm calling a complicated second layer set of metrology, you start to think about, well, you know, if I start to take these pieces, these individual piece parts that I put together, and I start to put them into an assembly, we want to start thinking about measuring those subassemblies to verify that those components that we've created are actually assembled correctly. So we start to think about some sort of subassembly performance, and you know, this would be in the case of what I was showing a few slides earlier. You're talking about your objectives or your tube lenses, and with that, you know, it becomes a little more difficult to say, well, what do I need from these different components to achieve the performance at the end of the line? And if we're thinking of this in terms of the microscope, well, what kind of wavefront performance do I need from my objective to achieve the resolution that I expect? That there's sort of a separation, I'd say, between, you know, this component wavefront error and resolution metrics in terms of, if I'm sort of keeping with this microscopy theme, it can be applied to imaging applications, optical imaging applications, and then other applications. So if you're just delivering light in an optical system, there's analogs. It's sort of like, well, we have our end system metrics, but then we want to know what performance we need out of these different components. And so, you know, if we have a nice high resolution. We want a nice high resolution image, or it doesn't have to be high resolution. It just needs to be achieved against whatever your imaging criteria is supposed to be for your system. What kind of wavefront error do we need from an objective, and how do we bridge this gap? So when we're thinking about metrology, and we need to come up with these answers, because if we're going to measure a subassembly, we want to know, if I measure 10 waves, is that good or bad for the objective? Or if do I need to measure a 10th wave of peak to valley wavefront error? And so you can do that during a design phase by basically coming up with a tolerance analysis to bridge this gap. You sort of feed in your nominal design, you have your tolerances of all your piece parts, and the tolerance analysis generally takes all that and perturbs the optical design to generate a statistically significant amount of Monte Carlo files. And then you can look at those outputs and say, oh, great. Now I have a relationship, and that's what that plot on the right is, the output. It's a representation of all these Monte Carlo trials. You have a relationship between your full system performance and your subassembly wavefront error. And so you can take that and you can start to use that to come up with performance targets for your metrology system when you're doing your design, because you don't want to be sort of at the end of your development and say, okay, well, my system doesn't pass, and then you start measuring things and you're like, well, I don't know, this tube lens has this wavefront error. Oh, now I need to go do that analysis and figure out what it was. You want to do it back in the beginning when you're doing the development, because you can also feed that back into the development to help you design better. But data like this helps provide in-process performance targets to help you build confidence that when you build these components and you get to the end of your assembly, you're building confidence that you're going to have a performing system. Also, in a production setting, or when you're doing prototyping, if you start measuring something and you see it doesn't pass, it's not meeting the specification, you can sort of halt your process right there before you get to the end of the road and say, hey, there's something wrong with this component. Either there was an error in the assembly, or there's a non-conforming part that maybe you missed in an inspection step, or maybe you didn't consider measuring that because of you had high confidence or that that performance spec was going to be achieved in inspection. So this data can help you catch those things early in the build process, or at a point in the build process where it doesn't affect the end result and will result in saving you time and money. It also helps you get the chance to rework components and feed it back in so that you build a system that will perform to your expectation at the end of the build. So if we're thinking about, this, what am I going to measure? And we're thinking about metric targets for metrology. You want to do that in early development phases. You want to do that because it helps you determine, what tools you might need, but it also helps you build this metrology foundation that'll support a well-performing system at the end. Metrology can, when you think about metrology early on, you can immediately think of, okay, well, I'm going to measure, piece part components, and I'll measure, mechanical dimensions or lens parameters of an assembly. And that is something you absolutely should do at an incoming inspection. But it may not be as obvious that, if you're building subassemblies, if you have an optical relay in the system, you will want to figure out, like, what about that relay is worth measuring so that you can yield a an appropriately performing product or prototype at the end of your build phase. And in the design phase, you can leverage the design and modeling work to answer those questions, figure out what metrics are you looking for looking to achieve when you do your metrology during your prototyping phase. And so, and specifically tolerancing analysis is one example of something that can bridge that gap between, you know, final system performance and looking at design files and say, okay, I know that for this statistical ensemble of systems that have this kind of performance, I need this kind of performance from your subassembly. Now let's move on to sort of a design and prototyping phase. So you've gotten out of your sort of early development, you figured out, you know, what your system is roughly going to be. Maybe you haven't done a lot of design, or you haven't done your critical design work yet. You know what you're going to measure, but then it's worthwhile while you're doing the real critical design of your system to figure out how I'm going to measure it. Now, this is also has sort of like a pretty straightforward thought about how you're going to measure a bunch of different components. There's lots of metrology tools that exist out and optical metrology tools that exist out in the world. You have optical comparators and calipers and CMM machines that can measure dimensions and different mechanical components. You have wavefront sensors, interferometers, MTF benches, other optical metrology tools that can measure components. And then there's even things like power meters and spectral sensors or spectroradiometers that can give you information about your different items you're going to interrogate. But you may also need to create custom metrology tools to measure your system. And so in this section, I'm going to go through and talk a little bit about you know, our experience with developing some different kinds of custom metrology tools and what that experience is like and how we came about that and why is that important. Because you can do a lot with, you know, sort of these kinds of off-the-shelf things, and you can do a lot of component measurement pretty in a straightforward manner. But once you get past the sort of component measurement, there's a question of when you get to your subassembly, you can do some analysis or some metrology on it with off-the-shelf tools. But, you know, if you're talking about subsystems or other things, you may not have a tool that measures what you're looking for very, very well. I do want to take a sort of like a quick aside and say that when you are doing a development and you're doing a design and a critical design, you should really think about fixturing, especially if you're going to be using sort of like interferometer, wavefront sensors, or things like this. Here's a picture of a wall at our facility here with our, I think Rick mentioned our IQ lab, which is our image quality testing house that we have at Optikos. And we sort of have boatloads of fixtures that we have designed over the years and had made to test all sorts of different kinds of lenses. And I think it's important to think about fixturing when you're doing the design, when you're in your design phase, because that might, thinking about how you're going to hold something or what you need to do to your optical assembly to be able to hold it when you're doing your test is very important. It's horrible to get to the end of your development where you're in your prototyping phase and you're testing something and you haven't really thought about your fixturing, and maybe you have a small lens assembly and you're messing around with a 3-jaw, like 3-claw chuck or 3-jaw chuck, trying to mount something in front of a interferometer, and you find out you don't have the right degrees of freedom to align something, and then all of a sudden you've got to go back and you got to wait and design something. You're losing time, you're losing money. That could have all been resolved and designed neatly and shown up with your prototype components if you had done all that during the design phase. So I would not discount thinking about fixturing design during your development. Don't leave it to the end. And sort of along those lines, often, you can have interferometry, you can have wavefront sensors, you can have other sorts of what you could call off-the-shelf metrology tooling, MTF benches and things like that to measure components. But I think in the years that I've been in the business and thinking about metrology, almost always a lot of applications end up coming up with some form of custom metrology setup. Now, many of these custom metrology setups may implement off-the-shelf components, but you want to give careful forethought into developing metrology tools during your design phase, because in the end, it's going to just save you so much time, make your life easier, and really speed the process when you're doing testing. And so I want to show a couple of examples of what I'm talking about. I had to find some way to get this into this talk because for some reason I think this is so cool. This is a Google Earth image of a test target that exists out in Eglin Air Force Base in Florida. And what it is a huge patch of asphalt in which a bunch of resolution targets were painted down. And I think it's pretty obvious that the idea is here that if you're flying something over this patch of ground, you can take a bunch of images and hey, you've got yourself sort of a very, very basic or very straightforward metrology test setup. And I mean, this is sort of an extreme case, but you can go online and from different vendors, you can buy, resolution test targets to do the same thing, and you can put them up on your wall, and they're very handy to do full system testing or sort of quick tests when you need to and you have one available. But maybe there's a case in which that doesn't really work for your form factor. You can be testing a camera and you can have, maybe you have an aerial imaging system. That's just a generic camera clip art that I have on here, but let's pretend it's a really fancy aerial imaging system. And you want to test in the factory. And, this is a case where you're going to need potentially some sort of custom metrology to do that. You could use an MTF bench, but maybe you want to have something that allows you to take a robust data set in one snapshot. And so what you could think of is, let's consider a multi-collimator projection system. Now, this happens to be something that we sell as a product, but the idea is that, depending on the constraints in your system and the thinking, you might want to design something that's a series of collimators to project a series of targets across a full field of view into your camera. And in a production setting, this is absolutely what you'd want. It's more compact, takes up less space. It takes up less facility space, so you don't have to pay for the overhead on rent for that area. And it'd be hard to integrate something into a production line that is some gigantic target. It's easier to make some sort of really small assembly. And so this is a situation where custom metrology can save you on money and, in this case, I guess, space. Another example of, a custom metrology, actually a couple versions of a custom metrology setup is, well, what if you want to test something that's an underwater camera? How do you test this? And I think there's a pretty quick, obvious way that we can, I'll show in a slide, but this is born out of a project where we designed a series of underwater imaging lenses. And the first thing you want to do when you test it is think about testing is like, well, let's build a pool of some sort and put some targets in there at the right conjugate distance. And we can do that, and you can measure resolution in the environment that the camera is supposed to be used. And so you can see a little bit of the camera in there. But, you know, it's a big tub of water. That's not great if you are requiring an alignment step of your lens assembly or lens to camera alignment, or you need to do 100% inspection of your camera assembly. A gigantic pool in your factory, well, it's not gigantic, but it's definitely pretty big for what anybody would probably expect in a manufacturing environment, doesn't seem like the greatest idea. And so you'd want to think about, well, can I do something during my design phase to come up with something that's more friendly for a manufacturing environment? And that's exactly what we did. Now, during prototyping and the development, we did both of these, but it's sort of a stepping stone from the water bath pool test to this sort of fully in air test. We were able to develop a test fixture that basically fit on a tabletop, took up a lot less space. I say easier to use because you didn't have to maintain the water in a water bath over time, or drain all the water and then pour water back in every time you wanted to do a test. And it also had a much lower risk of flood, which I don't know, when I think of something like that, that's always when I'm thinking of catastrophe, is like, am I going to flood my lab space? That'd be horrible. So, but you want to think about this during the design phase. You don't want to sort of tack it on at the end and say, oh no, we got to create a pool, or oh no, this isn't going to work because we can't have a pool. We need to come up with a sort of in-air equivalent test of this system to make it work. So if we're going to talk about what am I going to measure, or how am I going to measure different metrics that we've figured out during our early design process, component metrology is pretty straightforward. A lot of off-the-shelf tools exist. You do always want to think about fixturing, because you want to think about fixturing up front. Otherwise, you're going to lose a lot of time trying to cobble something together that maybe doesn't have the right degrees of freedom, and then it's just a mess, and all of a sudden it's leaking into how good is your measurement. You want to design those things as early as possible, or when it's reasonable. And then for your subassembly and full system testing, often there's going to be some form of customization. If you have an aerial imaging system and you want to project a bunch of targets into it to do a full field test, you might need to come up with some custom collimator assembly, or you can come to us. Or maybe you have a piece of metrology, you have an interferometer, but you have a folded system, and so you're going to need to come up with a set of tooling to hold your system, and then hold your reference sphere, or whatever your reference flat, to do your interferometry correctly. And you want to be thinking about this as you're designing your system. You don't want to wait until the end, because then all of a sudden you've built your prototype, and then you're adding on another whole development phase just to build your metrology system, develop your metrology at the end of your prototyping phase, and you're sort of like lost in the lurch. Now, let's say you've done all this metrology, and I do want to bring this up, and you still end up with an underperforming system. It's like, you've done your design work, you've run your project, you've done all this great metrology, and then at the end of you get your prototype together, and then you do a measurement, and it doesn't meet the performance you expect. Your manager is going to come to you and start hollering at you. We paid for all this metrology. You did all this in the development, and now it doesn't work. It's useless. And I'd argue, I mean, it's hard to, until you've experienced this a few times, I'd argue you're still better off than if you'd done little to no metrology. And that's because if we, I don't know, hypothetically want to think about, let's say we have some system that we've created and it has 10 parameters you've measured, and you knew about 9 of those parameters, and you've done metrology on those 9 parameters because you have a robust metrology plan. All of a sudden you can look at those 9 things and you immediately know from your design, oh, these all worked, or these were all in spec. These are things that aren't contributing to the problem. And then you are just left to figure out what is that 10th parameter. If you had done little to no metrology, you could be doing, in the case of this example, 10 times more work to figure out what's wrong with it. And then you can extrapolate that to an optical system. If you think about just the lens on its own, it has 2 radii of curvature, it has a center thickness, it has a diameter, there's wedges, there's irregularities, there's indices of refraction, there's the Abbe number. That's nearly, for one lens, that's almost 10 parameters that you're thinking about. You throw a bunch of lenses in there, all of a sudden you have dozens of parameters that could be contributing to your system, underperforming system. But if you have done your metrology, you don't have to think about those at all. You can focus on other areas. Maybe there was some sort of manufacturing issue that you didn't consider, an assembly error that you need to think about. But in the end, if you have robust metrology, you have, while it may not seem like it at the time, if you have a system that isn't exactly working, you're already ahead of the game compared to the alternate universe version of you that hadn't done any metrology. Now, you've done your prototyping, you've done your design work, you have your metrics sorted out, you have all this metrology figured out, and you're transitioning to your production phase or your manufacturing phase. And there's a question is, do I have enough metrology still? Do I have too much metrology? Do I have too little? Do I have the right mix of metrology? And I am going to stand on the shoulder of giants and cop out a little bit on this section, because we actually last year in the fall gave an entire webinar on metrology and manufacturing that I'd urge you to view if this is something that's of interest to you, because in the end, you know, a lot of what I said is leading up to this is going to be the same. You want robust metrology. You may not want the same mix of metrology, but what it comes down to is when you're in production and you're doing assembly, you want to think about, again, you know, these sort of simple metrology steps. Your incoming inspection, you want to confirm that the material that you're receiving in is good. You can do that either by trusting on vendor performance reports. Maybe you want to do spot checks on that. Maybe you want to do your own verification of that if it's a very critical parameter for your end system performance. You want to do a lot of in-process inspection. You want to look at sub-assembly performance, because, you know, you may have the parts all right, but if somebody put something in wrong, God forbid, you have a lens, you designed a lens that looks nearly biconvex, but one radii is off from the other, and somebody puts a lens in backwards, you want to catch that before you get to your final test. It's a good way to catch assembly errors if there are any, and it helps build confidence that once you get to the final functional test, that you're going to have a system that performs the way that you want. And then, I've already said it, you want to have final functional testing at the end of your production line. That is sort of like your last check to say everything is right and your product is good It helps you avoid anything that may have somehow slipped through. And also, by collecting this data and monitoring it, you can watch for trends in your performance or your production cycle, and you can see, oh, is something starting to happen with my assembly process that's making it start to trend in a direction where I might be able to predict that, oh no, I'm going to start having failing units. And so in a manufacturing setting, it's a lot of the same story, same themes. By having a robust metrology plan and the right metrology mix, you're going to catch issues early and identify issues to help keep you on schedule. You're going to provide more consistent performance, and more consistent performance. If you have a lot of variability in your process, you may have a lot of like fallout or loss, and that translates to cost. And so by having good metrology, you can minimize, your scrap in your system, or you can minimize losses in your production cycle, and then you maintain quality. You have consistent product that's going out that has the same sort of performance, and that speaks to, you don't want to have poor quality product. You want to have metrology that tells you that what you're sending out the door is the right thing and the right thing for your customer. So here's just a brief summary that is pulled out for manufacturing. It's the same thing. You want to implement inspection steps. You want to make sure that you have the right inspection metrology, and there's different devices that you can use for optical metrology in manufacturing. You want to pick the right ones for your needs. And I really strongly suggest watching that webinar, because there's lots of good stuff there that I would have certainly run out of time to talk about in this webinar. So, in summary, if we think about the three questions sort of posed early in the beginning about what should I measure, how should I measure it, and do I have enough metrology? Early design phase, you want to think about what parameters should I be measuring. This helps tells you what tooling you're going to need. But you also want to think about, in process, start to develop an idea of what in process steps, what sub-assemblies you want to test in your build cycle of either your prototypes or your manufacturing, because you want to build this sort of, you think of the house analogy again, you have these building blocks of metrology that ensure that in the end your product or your item that you've built is performing the way that you need it. How you should measure it is all about, picking the right metrology tools. In the end, there's a lot of existing metrology tools that are going to be obvious to people that you're going to need to measure different component specifications or even sub-assembly specifications. But at some point, you're going to need to most likely do some customization depending on what your application is. You're going to need to tailor the metrology to match what you are designing. You don't want the metrology tool to determine how you're going to design your system. And then when you get into your production cycle, you need to think about the kinds of metrology you want to implement through your manufacturing cycle to ensure that you have the best outcome for your production cycle, so you can track fallout, you can track trends in your performance, you can catch issues early in the production phase instead of at the very end, because if you catch them at the very end, that's when you're going to lose the most money in terms of your manufacturing cycle. So I want to circle back to this. The bottom line is really a metrology mindset is going to save your project. And you are going to eliminate confusion during your development, prototyping, and build processes. You're going to get consistent outcomes for your prototype builds and production. Both of those things are going to lead to less downtime, and less downtime or less time troubleshooting means you're going to save money. And who doesn't want to save money during your development? More budget is great, or recovering budget is absolutely wonderful. With that, I'd like to end. Thank you.
Thank you, David, for that great presentation. We now have time for a few questions before we wrap up. If you haven't already, please type your questions or comments into the chat box. The first question I have here is, traditional image processing methods often fail in underwater conditions. How is it countered?
I'm not quite sure what's being asked there. I think I can talk about what we've done, and hopefully maybe that'll answer the question. You know, in underwater imaging, there are, in our application, what we did was came up with an in-air test to verify the system's performance. I think that is really to validate that the camera system itself was performing the way it was expected. So really looking that the resolution or the distortion that you had in your system is working. If the question is more aimed at trying to figure out, you know, how do you get around effects like turbulence or absorption or scattering in water media, that's an interesting one to try to solve. I mean, that's where you'd want to probably try to simulate what happens in the water, either with testing in a pool, which isn't a great approach, but you could also consider thinking about, you know, how do you take those effects that exist in the water and basically replicate them in another medium accurately enough to help evaluate your system performance.
Okay, great, thank you. The next question I have here is, how did you know the replacement underwater metrology system provided results similar to the in-water test system?
A lot of questions about the underwater testing. Struck a nerve. So it was basically through a correlation study. And I'll have to dive a bit deeper. Wow, no pun intended there. We ran a resolution image quality correlation study between the in water versus in air test system, and really the idea is that we wanted to replicate the effective conjugate shift that the removal of the water incurred, and sort of compensate that with presenting targets at a different conjugate. We've done similar things also with other imaging devices where they're expected to be used in some sort of immersion condition, and it's not always beneficial. It's not great to always test in immersion, although our end test in this other application is an immersed situation, but we'll do an in-process test where we replace the water with a equivalent optical path difference of another material to simulate the water, and have found do sort of correlation studies to say that, you know, we're getting results that are identical or nearly identical enough that it makes sense for us.
Great, thank you. The next question I have here is, how does one choose between a bottom-up or top-to-bottom approach to apply metrology in the pre-development stage? Does Optikos use a mix of both?
I think we use a mix of both. I mean, it's sort of like when we have a project, and I hope I'm interpreting the question correctly. If you're doing a development, it's sort of like you always have some sense of what the end performance metric is going to be. If you're making an imaging lens, you know something about the image quality is going to be what you want to measure, and that's going to come right from your initial specifications. And that's sort of like where the end is. Your end goal is telling you what you want to do. You don't really need to do too much development unless you need. Well, you don't need too much development. On the other hand, as you're going through your development cycle and you have these different components, and I'm leaning heavily on the microscopy example here, is that you're going to have, that in the end you want resolution, but you have a tube lens and an objective, and you can measure those two components independently. And so figuring out what that I think is sort of where I would say the end resolution is what I'm interpreting as the top-down approach. The bottom-up is looking at the individual components. What kind of performance do I need out of the tube lens or the objective to yield that resolution? I mean, it also depends on how you're approaching your optical design. If you have, I guess, if you have a criteria where you say, I need diffraction limited imaging, there's an approach to say, well, I need to just make everything in your system diffraction limited. That's an easy way to go about designing a system, but it also can put constraints, especially in microscopy. It's sometimes easier if you can share aberrations, and then that's where you got to do your analysis and say, well, what am I really looking to get out of my objective when I test it?
Okay, well, great, thank you. The next question I have here is, how can application level image quality requirements be translated into measurable, traceable metrics at the earliest design phase?
I guess it depends on what the application level requirements are. If you're talking about something, if you're talking about like MTF or modulation transfer function, there's MTF benches that you can buy to do that testing directly. So that sort of, if your end performance requirement is MTF, you can measure MTF. If your end performance requirement is, and I'm thinking about image quality, so I'll say like point spread function, or let's just say point spread function. That becomes a little bit more difficult to evaluate. If you want to directly measure point spread function, you need to present a sub-resolution target. So if you can present something like that, and if you think about an MTF bench, hopefully people are somewhat familiar with what an MTF bench is. It's easy to present an unresolvable target and then just take an image of that to do your point spread function. If you're talking about something in microscopy, it's difficult because especially for high resolution microscopy, you're probably looking at something that's like a single molecule or unresolvable fluorescent bead, and that can be sort of a pain to measure in high NA applications. And so then in that application, you'd probably want to try to translate that into a different metric like MTF, although measuring high NA microscopes using MTF has its own challenges. Or you can translate, try to translate your point spread function to a wavefront error metric, which in our experience is what a lot of people do.
Okay, great, thank you. The next question I have here is, how do you determine whether the test setup measures correctly? Do you use audit lenses?
Yeah, and actually that's validating, verifying your test setup is critical. I can talk about what we do in terms of our metrology instruments that we make, and that is, we create some sort of audit lens or some sort of lens that you can use to confirm its performance on a different device and then measure it in your test setup to say, yes, this makes sense. And so that's usually what I consider a valid approach. If you have a way to provide sort of a traceable measurement back to some standard, like if you're developing a spectrometer of some sort, you can think about, well, what are things that I can measure that are traceable so that I can say that my performance is correct. This is a super important question when you're developing any sort of custom metrology. How are you going to trust that the measurements you're getting are correct? You don't just want to put something together and assume it's giving you correct results. That gets you into a lot of problems. So I would say, yeah, for some systems, especially if we're talking about image quality or something like that, it's you can use something like an audit lens, but you need to design the lens and then verify everything about the lens so that you know that the performance you're going to get out of the lens, it's going to yield you need to correlate all those things together so to know that the measurement you do on whatever test bench you have is the right answer.
Okay, the next question I have here is, for a complex optical system, can you comment on the trade-offs between designing independently corrected modules or testability versus optimizing performance across the full system, but without subassembly testability?
I mean, I'm always going to lean towards it. You can try to design your system perfectly and assume that everything is right, but I don't know. I wouldn't want to just design everything perfect. I think it's still worthwhile testing things to make sure that doing in-process testing until you have built confidence that the components that you're getting or that your assembly process is robust and not introducing any errors. Because you can go through a build and maybe all the piece parts are perfect, but maybe there is something in your assembly process that is changing the performance or the parameters of some system. The easiest thing that comes to mind is you mount a lens and you think your mounting is doing nothing to the lens or even a mirror. This is a classic thing with bonding mirrors into systems. How you bond the mirror distorts the mirror surface. So your mirror on its own has perfect wavefront. It's like, I don't know, better than 100th wave, let's say, but then you bond it into something, and that act of that manufacturing step distorts the surface, and all of a sudden your entire system performance is garbage. And it's just from an assembly step. Everything else you've designed in the system is perfect, but and the component you received into your build process was, quote, perfect, but the assembly process, it was flawed and causes problems. So I would always err on the side, especially at prototyping, of just always having inline metrology until you have built confidence that your build process is robust.
Okay, thank you. The next question I have here is, what strategies do you have for translating qualitative criteria from customers into quantitative measurable criteria?
Oh man, that's a good one, and I don't know how to answer that concretely. I mean, it comes down to really having a conversation with your customer about what they want, because they may have a criteria that is, let's try to come up with something that I want the image of the sky to be blue. That is an admirable goal for an imaging system. And so then it becomes a discussion about, well, what do you mean by blue? Do you mean I just want it to only pass 350 to 400 nanometer wavelength light and suppress all the other wavelengths? It may come down to some experimentation to try to bridge that gap from something that is sort of qualitative and somewhat ambiguous into something that's a concrete specification that you can measure concretely and reliably. So I think it really comes down to communication with your customer and educating them on what their qualitative spec means versus quantitative metrology.
Great, thank you. The last question I have is, in complex lens programs, what leading indicators in metrology data signal downstream image quality risk?
I would have to say, it depends on the project and what kind of metric you're looking for at the end. But often what I find is, in my experience, is, wavefront error is sort of like the big thing everybody talks about, and is something easy to design against. And I'm thinking in lens design software. You could, I know a lot of people talk about, spot size when we think about some lens design software. That's, looking at the spot size is good too, but that's not something, in terms of the software package I'm thinking of, is not something that you really measure. Wavefront error is something concrete that you can measure, and so that's a good thing to keep track of, to say, when you're doing a design, if I'm going to have good image quality at the end of the development, I want to track wavefront error, I guess.
Okay, great, thank you. If we don't get to your question today, don't worry, we'll follow up with you via email. And if you think of something later, feel free to reach out to us at webinar@photonics.com. Before we go, I'd like to thank our presenter one last time, David Biss, and all of you for joining us for Metrology as a Mindset, Engineering for Success. This webinar was presented by Optikos and hosted by Photonics Media. Thank you all so much.